Have you ever just looked up at the night sky and wondered what you're really looking at? Well, today, that's exactly the journey we're going on. We're going to start with those familiar lights right above us, and then we're going to zoom out and out and out, all the way to the edge of what we know.
You know, the material we're looking at today opens with this really simple thought, and it just perfectly nails that feeling, doesn't it? It's that sense of awe, that thing that connects all of us when we just stop for a second and look up. So you look up there, and it's filled with all these tiny, shining objects, kind of like someone scattered diamonds across black velvet. But if you look really close, you'll notice something. Some of them twinkle, right? And others just have this steady, solid glow. That one little observation, well, that's the key to figuring out what's a distant sun and what's a world just like ours. Okay, but that brings up a pretty obvious question. All those thousands of lights, they're still up there during the day. So where do they go? Why can't we see them? Well, the answer is actually really simple. Our sun is just so incredibly, unbelievably bright that its light just washes everything else out. It's like the biggest spotlight in the sky, and it completely overpowers all those other little lights. And you can actually see this for yourself. Imagine you're in a pitch-black room. You take a flashlight and shine it through a piece of paper with a bunch of tiny holes in it. On the wall, you'd see this cool field of stars. But then, what happens the second you flip on the main room lights, your sun? Poof, those little dots just vanish, totally drowned out by the brighter light. So, all this stuff we see up there, the sun, the moon, every single one of those twinkling or glowing dots, what do we call them? Well, the official term for all of them is celestial bodies. Okay, so let's get back to that twinkling thing, because it's super important. Those twinkling lights, those are stars. They're these gigantic, hot balls of gas that are making their own light. But the ones that have that steady glow, those are planets. They don't make any light at all. They're just reflecting the light from our sun, just like our own moon does. And get this, our sun is a star, and we know how huge it is. So why do all those other stars look like tiny little pinpricks? It's just distance. That's it. It's all about how far away they are. Think about an airplane flying way, way up. It looks tiny, right? It's the exact same idea, just on a cosmic scale.
Forever, people have been looking up at these same stars and connecting the dots, making pictures in the sky. We call these patterns constellations. One of the most famous is Ursa Major, which you might know as the Big Bear. And a part of that constellation is probably something you've seen before, the Big Dipper. Now, for centuries, one star was maybe the most important of all, the North Star, or the Pole Star. Since the Earth's axis points right at it, it looks like it never moves, while all the other stars seem to circle around it. For ancient explorers and sailors out on the open ocean, this was their GPS. It was their one constant, a true celestial compass. Okay, let's zoom in a little bit. From all of deep space to our own little neighborhood. This is the solar system. You can think of it as our solar family. You've got the sun right in the middle as the head of the family, and then you have 8 planets, their moons, and a bunch of other stuff like asteroids and meteoroids all orbiting around it, held together by the sun's gravity. And just to give you a little perspective here, even though the sun is our closest star, it's still about 150 million kilometers away from us. Just try to wrap your head around that number. It's mind-boggling. So how in the world do you remember the order of all 8 planets? Well, there's a classic trick for that. My very efficient mother just served us nuts. It's a super easy way to get them all in line. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. Okay, this table is where things get really interesting. Just look at the insane differences here. A year on Mercury is just 88 of our days. But then you go way out to Neptune, and its year is 164 times Earth years long. And then look at the day lengths. Venus is crazy. Its day is actually longer than its year. But then Jupiter, the biggest planet, spins so fast its day is under 10 hours. Wild, right? And then there's us, our home, Earth. It's truly a unique planet because it's in this perfect Goldilocks zone. It's not too hot, not too cold. It has liquid water, and it has an atmosphere with the air we need to breathe. All the ingredients for life are right here. And from way out in space, because of all our oceans, it's just this beautiful, shining blue marble. Of course, we can't talk about Earth without talking about its buddy, the Moon.
It's our one and only natural satellite. The reason it looks so huge in our sky isn't because it's actually that big. It's just that it's right next door, cosmically speaking. It's our closest neighbor.
You ever wonder why we only ever see one side of the moon? You know, the man in the moon is always the same guy? Well, it's not a coincidence. The moon is what we call tidally locked with Earth. It takes the exact same amount of time for the moon to spin once as it does for it to go all the way around us, about 27 days. That perfect timing keeps the same face pointed at us, always.
Now, besides the planets and moons, our solar system is also full of, well, rubble. Asteroids are basically chunks of rock and metal. Think of them as the leftover construction material from when the planets were first forming. Most of them are hanging out in this huge asteroid belt between Mars and Jupiter. And then you have meteoroids, which are even smaller bits of space rock. And every once in a while, one of them will cross paths with Earth and zip into our atmosphere. It's moving so fast that it burns up from the friction, creating that amazing flash of light we all call a shooting star.
So, we've covered our solar system, but it's time to zoom out again. Way out. Our entire solar system, our sun, our planet, everything, is just one tiny, tiny little speck inside a much bigger structure. Our home galaxy, the Milky Way.
So, what is a galaxy? It's a gigantic system with billions of stars, along with these massive clouds of gas and dust, all held together by gravity. I love this. In ancient India, when people looked up and saw that bright band across the sky, they imagined it as a river of light, or Akashganga. How beautiful is that? And now, for the last biggest zoom out. What could possibly be bigger than a galaxy full of billions of stars? The universe. And it is, quite simply, everything. All of space, all of time, and everything in it, including the millions and millions of galaxies just like our own Milky Way. So, let's bring it all the way back home. You are here. You're on a planet that's orbiting a star, that's in a solar system, tucked away in a quiet arm of a galaxy, which is just one of millions of galaxies in the known universe. When you think about that scale, that unbelievable size, where do you fit in? How does it make you feel? You know, have you ever pulled up a map on your phone and just wondered, how does it know exactly where you are? I mean, how do you find one single spot on this huge spinning rock we call Earth? Well, today, we're going to pull back the curtain on this amazing, invisible grid that covers our entire planet. We're talking about the simple but honestly brilliant system of lines and numbers that lets us navigate literally everything. So let's dive right in.
All right, here's the plan. First, we'll tackle the big problem. Just how do you describe a location? Then we'll build the solution, piece by piece. We'll look at the north-south piece of the puzzle, which is latitude, and then the east-west piece, longitude. After that, we'll see how it all comes together to make this awesome global grid. And stick around, because for the grand finale, we'll uncover a wild secret, how this same grid is the reason we have time zones.
Okay, so let's jump right in with the big challenge. I'm talking about a puzzle that seriously stumped people for centuries.
I mean, really think about it. How on earth do you describe one specific spot on a giant spinning ball? Imagine you're out in the middle of the ocean or a huge desert. There are no street signs, no landmarks, nothing. Without a system, you are completely and totally lost. And it was this exact problem that kicked off the search for a truly brilliant universal solution. So the first thing you need is a good model of the planet, right? And that's where the globe comes in. And here's a fun fact. Earth isn't a perfect sphere, it's actually a little squished at the poles and kind of bulges out in the middle. The globe shows us that. So think of this globe as our canvas. It's where we're going to solve this whole location puzzle. Okay, to even start drawing a map on this globe, we need a starting point, some kind of reference. And the very first one is the Earth's axis. Now, it's totally imaginary, but picture this line going right through the center of the planet, connecting the North Pole to the South Pole. It's like the skewer that our planet spins on. And just like that, it gives us our first two super important fixed points, north and south.
All right, we've got our north and south poles locked in. So now we can tackle the first half of the problem. How far north or south is something? And for that, we need to talk about latitude.
Now, this right here, this is probably the most important line on the whole planet, the equator. It's this imaginary circle that just wraps around the middle of the Earth, slicing it perfectly into two halves, the northern hemisphere and the southern hemisphere. We call it 0 degrees latitude.
This is our starting line. Everything is measured from here. Okay, so starting from the equator, imagine drawing a bunch of circles that run parallel to it, going all the way up to the North Pole and all the way down to the South Pole. These are our parallels of latitude. Think of them like rungs on a ladder. They let us climb up or down the globe and measure exactly how far we are in degrees from 0 degrees at the equator all the way up to 90 degrees at the poles.
But here's the thing. Just saying 20 degrees isn't enough, not even close. Take a look at this. Chandrapur in India and Belo Horizonte in Brazil, they're both at 20 degrees latitude. So what gives? Well, the crucial difference is one is 20 degrees north of the equator and the other is 20 degrees south. That one little letter, N or S, it changes everything. It puts them on completely different continents.
And get this, these imaginary lines, they have very, very real consequences. A place's latitude pretty much determines its climate. It's all about how much direct sunlight it gets. So you have the super hot torrid zone right near the equator, the much more moderate temperate zones in the middle, and then the frigid zones up near the poles, which are, well, you guessed it, frigid. Okay, so we've totally cracked the north-south code. We're halfway there. But that's only half the map. Now we need to figure out the east-west problem. And to do that, we need to introduce our second coordinate, longitude.
And here's exactly why we need it. Check this out. The Tonga Islands and the Mauritius Islands, they are both on the exact same line of latitude, 20 degrees south, but one is in the Pacific Ocean and the other is in the Indian Ocean. So if I just told you go to 20 degrees south, you'd have no clue where to go. We're clearly missing a piece of the puzzle.
So the lines we use for east and west are called meridians of longitude, and they're totally different from latitude lines. Remember how latitudes were parallel circles? Well, longitudes are semicircles. They all run from the North Pole straight down to the South Pole. The best way to picture it? Think of an orange. The lines of latitude would be like slicing the orange into rings, while the lines of longitude are like pulling it apart into wedges. They all meet at the top and bottom.
This created a big problem, though. Unlike latitude, which has the equator as a natural middle line, all these longitude lines are basically the same. There's no natural starting point. So what did they do? Well, they had a big meeting, and in 1884, countries from all over the world agreed that the line running through the Royal Observatory in Greenwich, London, would be our 0-degree line. We call it the prime meridian, and that became the official starting point for measuring everything east and west.
Okay, so now we have both pieces of the puzzle. We have our north-south lines, latitude, and our east-west lines, longitude. So what happens when we put them together? Well, this is it. This is the aha moment where it all just clicks. When you lay those latitude lines over the longitude lines, you get this, a grid, a beautiful, perfect network of intersecting lines covering the entire planet. And it works just like the graph paper you used in math class. Every single point where a latitude line crosses a longitude line, that marks one and only one exact spot on the surface of the Earth. And just like that, problem solved. Let's look at a real-world example. Take the town of Dhubri in Assam, India. Where is it? Simple. You find the line for 26 degrees north latitude, and you find the line for 90 degrees east longitude. The exact point where they cross? That's Dhubri. With just those two numbers, you can pinpoint its location on the map. It's that precise. But wait, there's more. Finding places on a map is just the beginning. This grid has a hidden superpower. Seriously, and it's something you and I use every single day, probably without even realizing it. It's all about telling time. And the way it works is actually pretty simple math. Check it out. The Earth spins one full circle, that's 360 degrees, in about 24 hours. Okay, so if you divide 360 by 24, what do you get? You get 15. That means for every hour that passes, the Earth rotates 15 degrees of longitude. And since our planet spins from west to east, the places to the east are always ahead in time, because they see the sun first.
So look at this. Let's say it's exactly 12 noon in Greenwich, right there on the prime meridian. Well, if you travel 15 degrees to the east, it's already 1 p.m. But at that exact same moment, if you go 15 degrees to the west, it's only 11 a.m. It's a simple, perfect rule. For every 15 degrees of longitude you move, the time changes by 1 hour. And this direct link between where you are east to west and what time it is, that's the whole reason we have time zones. To stop things from getting super confusing, big countries or regions just agree to use one standard time. So, for example, India's standard time is based on the line that's 82.5 degrees east of Greenwich.
Do the math, and that puts Indian Standard Time exactly 5.5 hours ahead of Greenwich Mean Time, or GMT.
You see this play out in the real world constantly. Think about watching international sports. A big cricket match might start at a perfectly reasonable 2 p.m. in London. But because of that time difference, that means it's starting at 7:30 p.m. in India. That's the global grid system working, right there, coordinating everything from business meetings to our favorite sports all across the planet.
So let's end with this one last thought. This amazing grid system, latitude and longitude, it was invented centuries ago for sailors trying to find their way across oceans using the stars. And yet today, the GPS in your pocket that guides you anywhere you want to go, it uses the exact same ancient idea to find your location down to a matter of feet. It's this centuries-old concept that's powering our supermodern world. I mean, how cool is that?
Have you ever just stopped and wondered about it? Why do we have day and night? Or how come summer always eventually turns into fall? Well, it all comes down to two huge moves our planet is making right this second. So let's dive into this incredible cosmic dance that basically runs our entire lives. So, what's the deal with day, night, and seasons? It seems like a pretty simple question, right? But the answer is actually this beautiful piece of choreography between the Earth and the Sun. It's a kind of cosmic waltz of spinning and orbiting that literally dictates everything, from when your alarm clock goes off to why you need to dig out that winter coat.
All right, let's kick things off with the motion we're all most familiar with, the one that governs every single one of our days. I'm talking about the Earth's constant, relentless spin.
Okay, so this movement has a name: rotation. The easiest way to picture it is to imagine a giant invisible stick running right through the Earth from the North Pole all the way to the South Pole. That's its axis. And our planet? It's just in a constant, steady spin around it, kind of like a toy top.
And this spin isn't random at all. It's incredibly precise. It takes almost exactly 24 hours for the Earth to complete one full turn. And that right there gives us our most fundamental unit of time, a single day.
Now, this constant spinning has one super obvious effect. As the Earth turns, one half gets bathed in sunlight. That's our daytime. The other half faces away into the darkness of space, giving us night. And that moving line that separates them, it has a pretty beautiful name: the circle of illumination.
Now here's where it gets kind of wild. Just imagine for a second. What if the Earth didn't rotate? Well, one side would be permanently stuck facing the sun, getting absolutely scorched in blistering, non-stop daylight. The other side would be locked in a deep, perpetual freeze. Our world, our life, it just couldn't exist.
Okay, so that's the daily spin that gives us our 24-hour cycle. But get this, while that's happening, our planet is also on a much, much grander journey. So let's kind of zoom out and take a look at the massive orbit that defines our entire year.
We call this second big motion revolution. So at the very same time our planet is spinning on its axis, it's also traveling along this huge fixed path, its orbit, all the way around the sun. It's multitasking.
Now, this big trip takes about 365 days and 6 hours to complete. To keep our calendars nice and tidy, we just round down and call a normal year 365 days. So what about those extra 6 hours? Well, they add up. Every 4 years, they become a full 24-hour day, which we add to our calendar as February 29th. And that gives us a leap year. Pretty clever, right?
And here's another key detail. This orbit isn't a perfect circle. It's a slight oval, an ellipse, which means our distance from the sun actually changes a little bit throughout the year. Now, you might think that's what causes the seasons, but the real reason is actually way more interesting. So if it's not about getting closer or farther away from the sun, what does cause the seasons? Well, it turns out there's one more absolutely crucial ingredient in this cosmic recipe: the Earth's all-important tilt. I mean, think about it. If the Earth orbited the sun perfectly upright, straight up and down, the climate would be pretty much the same all year round. No real seasons to speak of. So what's the secret ingredient that gives us all this variety?
And here it is, the secret sauce. The Earth's axis isn't vertical. It's tilted at an angle of 66.5 degrees compared to its orbital path. The main takeaway here is really simple. Our planet is always leaning as it travels through space.
And this, right here, is the most important part. That tilt is constant. As the Earth revolves around the sun, its axis is always pointing in the same direction out in space, right toward the North Star. This consistent lean is the true cause of our seasons. Let's see how.
So how does this constant lean, combined with a year-long journey around the sun, actually create our seasons? Let's take a quick trip through the year to find out.
This journey has 4 key moments that mark the changing of the seasons. You've got 2 solstices, those are the extremes, and 2 equinoxes, which are the points of balance.
It really is put perfectly here. The seasons don't change because the Earth gets closer to or farther from the sun. They change because the Earth's position in its orbit changes how the sun's light hits our tilted planet. It's all about the angle. Let's just compare the 2 extremes, the solstices. Around June 21st, the northern hemisphere is tilted directly towards the sun. The sunlight hits it like a focused flashlight beam, giving it concentrated energy and longer days, and that gives us summer. 6 months later, around December 22nd, that same hemisphere is tilted away. Now the sun's light hits at a glancing angle, spreading its energy out. That means less heat and shorter days, which gives us winter. And of course, for the southern hemisphere, the seasons are always the exact opposite.
So what about those in-between points? Well, those are the equinoxes. Twice a year, the Earth's tilt is kind of sideways relative to the sun. Neither the north nor south pole is really tilted towards it. And on these days, the sun's rays shine directly on the equator, and day and night are almost exactly equal in length everywhere on Earth.
These 2 equinoxes mark the beginning of spring and autumn. But remember, because of that constant tilt, the seasons are always opposite in the northern and southern hemispheres. So when it's autumn up north, it's spring down south, and vice versa.
So after all that, how do these huge cosmic movements connect directly back to you and your daily life? Let's put the whole formula together. It really all boils down to this simple cosmic formula. The daily spin, our rotation, gives us day and night. The yearly journey, our revolution, gives us the year. And when you combine that revolution with the Earth's constant, unchanging tilt, you get the beautiful cycle of the seasons. That's the whole recipe.
And that leaves us with one final thought. This whole delicate balance, rotation, revolution, and that very specific tilt makes life on Earth possible. But what if you could change it? If you could set a new angle for the Earth's tilt, what would it be? Would you make the seasons more extreme with a bigger tilt, or get rid of them almost entirely with a smaller one? It's kind of a wild thing to think about.
Have you ever stared at a map and felt, well, a little lost? Kinda ironic, right? Well, today we're going to unlock the secrets of maps. We're going to see how these incredible documents are so much more than just lines on paper. They're actually a powerful language for understanding and navigating our entire world. So let's dive in.
Okay, so let's kick things off with a little puzzle. Why can't a globe, that perfect round model of the Earth, show you how to get to the corner store? I mean, it seems like it should be the ultimate map, right? But as you're about to see, its perfection is also its biggest problem.
Here's the thing. A globe is fantastic for the big picture stuff. You want to see how continents and oceans relate to each other in their true spherical form? A globe is your best friend. But trying to zoom in on your town, or even just your neighborhood, it just doesn't work. For that kind of detail, we need to flatten the world.
But of course, flattening a sphere is tricky. I want you to imagine drawing something on a rubber ball. Got it? Okay, now in your mind, take some scissors, cut that ball open, and try to lay it perfectly flat on a table. What happens? That drawing you made gets all stretched and warped, right? It gets distorted. That is the exact problem mapmakers face when they try to put our round Earth onto a flat piece of paper.
And that brings us to the hero of our story, the map. A map is basically a drawing of the Earth's surface, or just a small part of it, that's been carefully designed to work on a flat surface. It is the brilliant solution to the globe's biggest limitation.
So, now that we know why we need maps, let's talk about the different kinds you'll run into. Because not all maps are created equal. They come in different flavors, you could say, each with its own job. Let's take a look at the 3 main types.
First up, you've got physical maps. I like to think of these as nature's own blueprints. They show you the physical landscape, the towering mountains, the deep oceans, the winding rivers, and the vast plains. It's all about the natural stuff, the physical features of our planet. Next are political maps, and these are probably the ones you've seen most often in school. They show us the world the way humans have chopped it up. Countries, states, cities, all with their neat human-made borders. They tell a story about history, government, and how we organize ourselves. And finally, we have thematic maps. These guys are the specialists.
They're built to show you information about one specific theme or topic. A road map? That's a thematic map. A weather map that shows you where it's going to rain? That's one too. Or even a map showing where all the forests are. They tell one very specific story.
So here's the cool part. It doesn't matter if you're looking at a physical, political, or thematic map, they all share a common language. And there are 3 fundamental keys to understanding this language. Once you get these down, you can unlock the story hidden in pretty much any map you find.
And here they are, the big 3. The essential components of every single map are distance, direction, and symbols. Think of them as the grammar of map reading. Let's break them down one by one, and we'll start with distance.
So let's think about this. How on earth do you fit an entire continent, let alone the whole world, onto a single sheet of paper? Well, the magic behind that trick is a concept called scale. It's how maps shrink reality down to size while keeping everything in proportion.
So what is scale, really? It's simply the ratio between a distance you measure on the map and the actual distance out there in the real world. You can think of it as the map's official shrink factor.
For example, a map's scale might tell you that 1 centimeter on the paper represents, say, 5 kilometers on the ground. And once you know that rule, you can measure any 2 points on the map and figure out the actual distance between them. It's an incredibly powerful little tool. Now here's the part that can trip people up, because the names seem backwards. A large-scale map actually shows a small area, like your town or village, but it shows it with a ton of detail. On the flip side, a small-scale map shows a huge area, like an entire continent, but with way less detail. Just remember it this way: large scale means large amounts of detail.
All right, that was distance. Our second key to cracking the map code is direction. I mean, a map isn't much help if you can't tell which way is up, right? To get our bearings, we use what are called the cardinal points.
If you look closely at almost any map, you'll find a little arrow somewhere on it, usually with the letter N at the top. This is the north line. It's your anchor. As soon as you know which way is north, you can figure out every other direction from there.
And those other directions are based on the 4 main or cardinal points. We all know them: north, south, east, and west. These are the absolute pillars of navigation on any map.
But sometimes you need to be a little more precise. And for that, we have the intermediate directions that sit right between the main ones: northeast, southeast, southwest, and northwest. Using these, we can pinpoint a location way more accurately.
Okay, so we've covered distance and direction. Our third and final key is symbols. And this is where maps really start speaking their own unique and surprisingly universal language. I mean, think about it. It's literally impossible to draw a tiny, perfect picture of every single building or road or river on a map. You'd run out of space instantly. So to solve this, map makers use a kind of shorthand: simple symbols, lines, and colors to stand in for all those real-world features.
And these are what we call conventional symbols. What's so amazing is that through international agreements, many of these symbols mean the same thing all over the world. So that little symbol for a post office or a church, someone in Japan will understand it just as easily as someone in Brazil. It really is a universal language.
Colors are a huge part of this language too, especially on physical maps. It's a pretty simple code. Generally, blue is always for water, brown is for mountains, yellow is for plateaus or higher flat land, and green is for plains. It's a super intuitive system that helps you understand the landscape at a glance.
So to bring this all together, let's make one last really important distinction: the difference between a map and a sketch. A sketch, like if you're drawing directions for a friend on a napkin, is just a rough drawing from memory. It is not to scale. A map, on the other hand, is always drawn to scale. And that precision, that commitment to scale, is what gives a map its real power.
So in the end, you see, a map isn't just a drawing. It's a shared story about a place, written in a language that anyone, including you, can now learn to read. By understanding distance, direction, and symbols, you have the keys. You can now unlock that story for any place on Earth.
Have you ever stopped to think about what really makes our planet, well, Earth? It's not just a big rock floating in space, right? Today we're going to dive into the 4 big systems, the major domains that all work together to make this the living, breathing world we call home.
So, what's the magic ingredient? What makes life on Earth actually possible? Well, it's not just one single thing. The answer is this amazing dance, this interplay between 4 totally different but completely interconnected systems. So, let's meet the team.
Okay, first up, we've got the lithosphere. The name comes from the Greek word lithos, which literally means stone. And that's exactly what it is. It's the solid ground right under our feet. We're talking about the Earth's crust, the continents, basically the very foundation of our planet.
Next, we have the hydrosphere. And you can probably guess this one. It comes from the Greek hudor, meaning water. This is all the water. Think about it. The deepest oceans, all the rivers, the glaciers, the ice sheets at the poles. If it's water, it's part of the hydrosphere.
Then there's the atmosphere. This one comes from atmos, the Greek word for vapor. And it's this incredible, invisible blanket of air that surrounds us. It's not just what we breathe. It's also this super important shield that protects us from all the crazy stuff out in space. And finally, bringing it all home, we have the biosphere. Bios, as you might know, is Greek for life. And that's the key. This is the special zone where the land, the water, and the air all meet up and interact to make life possible. It's literally where everything comes together.
All right, so now that we've met the whole crew, let's dig a little deeper into the first one. It makes sense to start from the ground up, right? So let's talk about the lithosphere, our planet's solid foundation.
So what are we really talking about when we say lithosphere? It's so much more than just rock. It's the planet's entire solid crust, and that includes those super important thin layers of soil that are packed with nutrients, the stuff that actually sustains organisms. And you can think of it as being split into two main parts. You've got the huge land masses, the continents, and then you've got the enormous ocean basins where all that water sits.
You know, to really get a feel for just how massive the lithosphere is, you just have to look at its most extreme points. The highest point on Earth, yep, no surprise here, it's Mount Everest, towering at an incredible 8,848 meters above sea level.
But check this out. The deepest point goes even further down. We're talking about the Mariana Trench in the Pacific, which plunges to a mind-blowing 11,022 meters below sea level. Just think about that for a second. The deepest part of our ocean is more than 2 kilometers deeper than our highest mountain is tall. It just goes to show you the wild, dramatic landscape of our planet.
Okay, so from the solid ground, let's dive into the world of water. We're moving on to the hydrosphere. And this one has a really interesting paradox at its heart. I mean, we all call Earth the blue planet, right? And for good reason. Over 71% of its surface is covered in water. So, here's the question. If there's so much water everywhere, why are we always hearing about water shortages? It just doesn't seem to add up.
Well, here's the answer to that puzzle. A whopping 97% of all that water on Earth, it's salt water in the oceans. You can't drink it, you can't grow crops with it. That leaves only a tiny 3% as fresh water. And get this, a huge chunk of that small amount is frozen solid in glaciers and ice caps. So when you boil it all down, the amount of fresh, accessible water we can actually use is just a teeny tiny fraction of the total.
All right, from the deepest parts of the ocean, let's travel all the way up into the invisible but absolutely vital domain that's all around us. We're talking about our protective atmosphere, that big blanket of air.
So what exactly is in this air we're breathing every second? You probably guess it's mostly oxygen, right? But look at this breakdown. A full 78% of it is actually nitrogen, which is super important for plants. Oxygen, the stuff we need to live, only makes up about 21%. And every other gas, we're talking carbon dioxide, argon, all of it, is crammed into that little 1% that's left over.
And this whole atmospheric blanket isn't just one big blob of air. Nope, it's actually structured in 5 different layers, stacked on top of each other. Down here at the bottom, that's the troposphere. It's where we live, and it's where all our weather happens. As you go up, you hit the stratosphere, then the mesosphere, the thermosphere, and finally, way out there is the exosphere. That's the very edge, where our atmosphere just kind of fades away into the blackness of space.
Okay, so we've looked at the land, the water, and the air. Now it's time for our final and maybe most important domain. This is the one where all 3 of those things come together to create the living world as we know it. Let's talk about the biosphere. This really is where it all happens.
Now, the biosphere isn't really a separate place you can point to on a map. It's more like a narrow zone where everything interacts. It's that critical sweet spot where the land, water, and air all meet and overlap. And it's in that zone that the magic happens. The conditions become just right for life to exist. I mean, think about it. From the deepest tree roots down in the soil to the birds soaring high in the sky, it's all happening inside this amazing interconnected living system.
Here's the thing. All these domains are connected in a really delicate balance. And it's a balance that, unfortunately, human actions can throw off pretty easily.
Let's take a clear example: deforestation. You know, when we cut down forests to get wood or to clear land for farming.
Well, the effect on the ground is almost immediate. See, without all those tree roots acting like a net to hold the soil together, that valuable topsoil just gets washed away super fast whenever it rains. It's a perfect real-world example of how an action we take in the biosphere directly messes with the lithosphere. It just hammers home how deeply connected all these systems truly are.
And those impacts just ripple out from there. Discharging waste materials, that pollutes the water, the hydrosphere. Emissions from our cars and factories, that pollutes the air, the atmosphere. And that buildup of CO2 in the atmosphere is what leads to global warming, which of course threatens the entire biosphere. You see? Every single action sends these shockwaves through the entire system.
So if there's one thing to take away from all this, it's this. These 4 major domains of Earth, the land, the water, the air, and life itself, they aren't separate things. Not at all. They are one single, massive, interconnected system. And it's all held together in this incredibly delicate balance. So the question we're left with isn't really if we should protect this balance, it's how.
Hey there, and welcome. Today we're going to dive into the absolutely incredible forces that shape the very ground we live on. You know, from those soaring mountain peaks to the vast flat landscapes, every single feature on our planet tells a story. So let's kick things off with a simple question. I mean, really think about it. Why isn't our world just a smooth, perfect marble floating in space? It's bumpy, it's rugged, it's got all these amazing features. And you know what? There's a fascinating reason for that. And here it is. This is the key. The Earth's surface, what scientists call the lithosphere, it isn't static at all. It's actually in a state of continuous, almost invisible movement. It's a constant process of being built up and then torn right back down again. So, here's our game plan for this explainer. First, we'll look at the fundamental forces at play. Then, we'll journey through the 3 major landforms. That's mountains, plateaus, and plains. And finally, we'll see how all of this shapes where and how we live. Okay, our journey begins with these 2 incredibly powerful processes that are in a constant tug-of-war, sculpting every single landform you've ever laid eyes on. This breaks it down beautifully. So on one side, you have these internal processes. These are forces from deep within the Earth that literally push the surface up, creating mountains and plateaus. But at the same time, you've got external processes, things like wind and water, that are constantly wearing the land down. We call that erosion. And then they rebuild it somewhere else by dropping all that material, which is called deposition. It's this amazing, endless cycle of creation and recreation. And that brings us to our first stop. Let's start at the highest points on the planet, the truly majestic mountains. So what actually makes a mountain a mountain? Well, generally speaking, it's a natural elevation that's over 600 meters, that's about 2,000 feet, high. They usually have a pretty small peak, or a summit, and a really wide base, just rising dramatically from the land around them. All right, so how do these massive structures even get built in the first place? Well, the basic idea behind how some of the world's biggest mountain ranges were formed can be explained with a really simple analogy. Just imagine taking a stack of paper and pushing it from both sides. What happens? It buckles and folds upwards, right? Well, that is pretty much what happens when the Earth's massive tectonic plates push against each other. The crust just bends and rises, creating these incredible folded peaks. It's a perfect example of the sheer power of those internal forces we were just talking about. But of course, not all mountains are made that way. There are really 3 main types. We just covered fold mountains. But then you have block mountains, which form when these huge blocks of earth get pushed up or drop down along faults in the crust. And finally, you've got volcanic mountains, which, you guessed it, are built up from layers and layers of erupted lava and ash. All right, pop quiz time. What is the tallest mountain on Earth? I'm sure an answer immediately popped into your head. But are you sure it's the right one? Because if you said Mount Everest, you're in for a little surprise. Now, while Everest is the highest mountain above sea level, it's not actually the tallest from its base all the way to its peak. The true champion is Mauna Kea in Hawaii. It's actually an undersea volcano, and when you measure it from its base on the ocean floor, it's over 10,000 meters tall, which is significantly taller than Everest. It's just that most of its incredible size is hidden beneath the waves. How cool is that? But you know, mountains are so much more than just beautiful scenery. They are absolutely vital to life on Earth. Think of them as massive water towers. Their glaciers feed the rivers that give us water for farming and for hydroelectric power. Plus, they're hotspots for biodiversity and, of course, huge hubs for tourism and recreation. All right, from the peaks, our journey is now going to take us to a different kind of high ground, the vast, flat expanses that we call plateaus. So a plateau is basically a tableland. It's an area of high elevation, but here's the twist. Unlike a mountain, it has a large, flat top. It stands way up high above the surrounding landscape, often with these really steep slopes on one or more sides. And just to give you a sense of scale, the Tibet Plateau is often called the roof of the world. It's the highest and largest plateau on the entire planet, stretching for thousands of kilometers at an average elevation that's actually higher than most mountains in Europe. And just like mountains, plateaus are incredibly useful. They are absolute storehouses of mineral wealth. A lot of the world's major mining areas for things like gold, diamonds, and iron are found in plateaus. And some, the ones formed by ancient lava flows, have this incredibly fertile soil that's just perfect for farming. Okay, now we're going to descend from the highlands to our final landform, the low-lying flat plains. And this is where the vast majority of humanity actually makes its home. So how are these huge flat areas even made? Well, it all comes back to that external process of erosion and deposition. You've got rivers rushing down from mountains, carrying all this eroded material like silt and sand with them. Then, when the rivers hit lower ground and slow down, they drop that whole load. Over thousands and millions of years, these deposits build up and up to create these deep, incredibly fertile plains. And this combination of fertile soil and flat land, that's the magic formula. It is perfect for farming, perfect for building cities, and perfect for creating roads and railways. It is absolutely no accident that the great cradles of human civilization all grew up in river plains. So let's bring it all together now and take a look at the direct connection between these different landforms and the patterns of human life across the globe. I mean, the contrast is just stark. Life in the mountains is often really difficult, right? The climate is harsh, the slopes are steep, there's not much flat land for farming, so they tend to be thinly populated. But plains, on the other hand, they provide pretty much everything we need to build communities. Fertile land for our crops and flat ground for our houses and roads. And that's exactly why they are the most densely populated areas on Earth. And that really brings us to our final thought. As we use all of these landforms, building our cities on plains, mining resources from plateaus, drawing water from mountains, we have a massive responsibility. These landscapes were shaped over millions of years, and this quote is a perfect reminder that it's our duty to be careful stewards of these incredible, life-giving features of our amazing planet. Welcome to The Explainer. You know, it's pretty incredible to think about a single country that has pretty much every landscape you can imagine. How is it possible for one nation to have the world's highest mountains, these huge, fertile plains, ancient rocky plateaus, and tropical islands? Well, today, we're going to find out. So let's start with just one number, 3.28 million. That's the area of India in square kilometers. We're not just talking about a big country here. This is practically a subcontinent. And that massive scale is really the key to understanding all the incredible diversity we're about to get into. So here's how we're going to tackle this journey. First, we'll get a handle on the country's huge size. Then we'll head north to that great Himalayan wall. From there, we'll come down into the river-fed heartland, cross the ancient southern plateau, and wrap up our tour on its beautiful coasts and islands. Okay, first up, let's really wrap our heads around the sheer scale of this place. Because a country's size and shape on the map, they aren't just lines, They really define its climate, its culture, and believe it or not, even how its people experience time. Just try to picture this for a second. A trip from the snowy peaks of Kashmir all the way down to the tropical beaches of Kanyakumari is over 3,000 kilometers. And going from east to west is almost the same distance. This isn't just big, it's absolutely continent-sized. Now, that massive east-west spread, we're talking almost 30 degrees of longitude, well, it brings up a really fascinating problem. If the sun is rising at totally different times across the country, how does everyone agree on what time it is? What this literally means is that the sun can be fully up for folks in the east, while the west coast is still completely dark. There's a natural time difference of a full 2 hours. So to keep things from getting chaotic, the whole country just agrees to use one single time zone, Indian Standard Time. And of course, a country this huge is going to have a lot of neighbors, right? India shares its land borders with 7 different nations, which creates this incredibly complex and dynamic frontier that has really shaped its history for centuries. All right, let's shift our focus now to the northern frontier. And calling it a frontier doesn't even do it justice. We're talking about a colossal wall of rock and ice that literally shapes the climate for the entire subcontinent. We're talking about the Himalayas. You know, the name itself really tells you everything. In Sanskrit, Himalaya translates to the abode of snow. It's just the perfect way to describe a mountain range that is forever covered in ice and snow. Now, here's something a lot of people get wrong. The Himalayas aren't just one single line of mountains. They're actually 3 parallel ranges, all running side by side. The one furthest north, the Himadri, that's the big one. It's got the world's highest peaks. Then there's the middle range, the Himachal, where you'll find all those popular hill stations. And finally, the southernmost range is the lower Shivalik. Okay, so imagine we're coming down from those incredible heights of the Himalayas. The whole landscape just flattens out into this massive green area. This is the Northern Plains, and it is the agricultural heart of India. So what's the secret to this region's incredible richness? It's all about something called alluvial deposits. Basically, for thousands and thousands of years, rivers have been carrying this superfine, nutrient-rich soil down from the Himalayas and spreading it all over this basin. It's like a gift from the mountains. These great rivers, the Indus, the Ganga, and the Brahmaputra, they are the absolute lifeblood of this area. They built these plains, and that amazing fertility is exactly why so many people live here. It's one of the most densely populated places on the planet. And where 2 of these mighty rivers finally meet the sea, well, they create something absolutely monumental. They join forces to form the Sundarbans, which is the world's largest river delta. Just incredible. All right, let's head south. As we leave those young, fertile plains behind, we're basically stepping back in time onto a much, much older landscape. This is the Peninsular Plateau, the ancient, rocky core of the subcontinent. And the name Peninsular Plateau gives you a huge clue about its shape. A peninsula is just a piece of land that's surrounded by water on 3 sides. And that's exactly what you see with southern India. It's framed by the Arabian Sea, the Indian Ocean, and the Bay of Bengal. The edges of this plateau are framed by 2 mountain ranges, called the Ghats. But here's the thing, they are not identical twins. The Western Ghats form this almost continuous, solid wall along the coast. But the Eastern Ghats, they're much more broken up and uneven. So this difference between the Ghats, it's a huge deal. It basically tilts the entire subcontinent. Only a couple of major rivers, the Narmada and Tapi, managed to push through that western wall and flow into the Arabian Sea. Most of the other big rivers, like the Godavari and Krishna, actually start in the west, but have to flow all the way east, across the whole plateau to drain into the Bay of Bengal. For our final stop, we're leaving the mainland behind altogether, because India's geography doesn't just stop at the water's edge, it extends out into the sea, with 2 very different and totally fascinating groups of islands. You've got 2 main groups of islands, and they couldn't be more different. Over in the Arabian Sea, you have the Lakshadweep Islands, and way out east in the Bay of Bengal are the Andaman and Nicobar Islands. One is a collection of tiny coral atolls, and the other is a chain of volcanic hills. The way the Lakshadweep Islands were formed is, well, it's just mind-blowing. They're not made of rock or dirt, they're made of life. These islands are basically the built-up skeletons of millions and millions of tiny marine animals called polyps, which accumulated over thousands of years until they finally poked through the surface of the ocean. So, from the highest peaks on Earth to islands literally built by microscopic creatures, it's clear India isn't just one landscape, it's a collection of many. This incredible physical diversity has been the backdrop for all of its history, its cultures, its languages. And that leaves us with one last question to think about. Does this incredible geography divide people, or is the shared experience of living in these wildly different places the very thing that unites them?
All right, welcome. Today we are diving into a really incredible natural story. We're going to look at how the powerful forces of climate in India create this stunning variety of plants and animals, and how they're all linked together in one massive interconnected system. I mean, think about it. How is this even possible? How can one single country have the freezing cold of the Himalayas? We're talking places like Dras and Kargil, and at the same time, the scorching, blazing heat of the Jaisalmer Desert. Well, the answer lies in this massive natural engine that drives absolutely everything, India's incredibly varied climate.
Okay, but before we go any further, we got to get one crucial thing straight: the difference between weather and climate. You know, weather is the day-to-day stuff. Is it sunny today? Is it going to rain? That kind of thing. But climate, that's what we're talking about here. It's the big picture. It's the average pattern over many, many years. I like to think of it as the personality of a place, not just its mood for the day.
So what's India's climate personality? Well, broadly speaking, it's a monsoon climate, and the word itself is pretty cool. It comes from the Arabic mausam, which just means seasons. And it's all driven by a pretty simple fact of physics, really. In the summer, the land heats up way faster than the ocean. This creates a massive pressure difference that literally pulls in these moisture-packed winds from the sea. And boom, that's what brings the famous rains that pretty much direct the entire rhythm of life there.
But just how important is this whole system? I mean, really, let's just stop and think about that for a second. What would actually happen if this massive engine just stopped? What if it failed for just 1 year?
The impact? It would be immediate, and it would be severe. You see, agriculture in India is so deeply dependent on these rains. So crops would fail, just like that. The water level in wells would plummet. The entire natural balance would be completely thrown off, leading to a much longer, much harsher summer. It really is that critical.
And this really shows you how the monsoon is like the director of an annual play, right? You've got 4 distinct acts. First, the cold, dry winter. Then comes the hot summer. Then, the main event, the rainy southwest monsoon. And finally, you have the retreating monsoon in autumn. This cycle, this play, it governs absolutely everything.
And if you zoom in on one of those acts, like the hot summer, you get these really specific, intense phenomena. For example, across northern India, people experience these intensely hot and dry winds called the Lu. It's a very real, very physical effect of the seasonal climate that you can actually feel.
So, here it is. Here's the crucial link. Think of climate as the very first domino. And the amount of rain it delivers, well, that is the single most important factor that decides what kind of natural vegetation, grasses, shrubs, trees, can grow in any given place. This is where the whole chain reaction really kicks off.
Want to see this in action? Let's start with a crazy extreme. On one end of the rainfall spectrum, you have a place called Mawasrim in Meghalaya. And get this, thanks to the monsoon winds slamming into the mountains there, this spot gets the highest rainfall not just in India, but on the entire planet, the wettest place on Earth.
So what does all that incredible amount of water create? You guessed it, tropical rainforests. We're talking forests so incredibly dense with life that sunlight often can't even touch the ground. And they're called evergreen for a really cool reason. Different trees shed their leaves at different times, which means the forest as a whole just always looks green. It's constantly alive.
Okay, so that's one extreme. But what about the complete opposite end of the scale? In places where there's hardly any rain, the plants can't afford to be lush and dense. No way. They have to be tough, they have to be clever, and they have to be built for one thing and one thing only: pure survival.
And the result? Thorny bushes. And these things have a brilliant adaptation. Their leaves have literally evolved into sharp spines. Why? Well, it drastically reduces the surface area, which minimizes how much water they lose to the hot, dry air. It's an absolutely crucial survival strategy that you'll see all over arid states like Rajasthan, Punjab, and Gujarat.
All right, so this table really pulls it all together nicely. Based mostly on climate and how much rain a place gets, you can see India's 5 major types of natural vegetation. We've already talked about the super dense rainforests and the toughest nails thorny bushes, but you've also got tropical deciduous forests, the ones that shed their leaves every year. Then there's the unique cone-shaped trees you find up in the mountains. And get this, incredible mangrove forests that can actually survive and thrive in saltwater. Amazing.
Okay, so the climate domino has now knocked over the vegetation domino. So what's the final piece in this incredible chain reaction?
It's the wildlife. Because each one of these unique, specialized forests creates the perfect custom-built home for a very specific community of animals.
And you can see this link so clearly when you look at some of India's most iconic animals. You don't find the Asiatic lion just hanging out anywhere, right? Its last wild habitat is Gujarat's Gir forest. The one-horned rhino? It roams the forests of Assam. And the elusive, almost mythical snow leopard, you'll only find it way up in the high-altitude Himalayan region. The habitat completely dictates who lives there.
You know, this biodiversity is so fundamental to the country's identity that its national symbols are pulled directly from the natural world. I mean, look at this. The magnificent tiger is the national animal, and the absolutely beautiful peacock is the national bird. They're both just these powerful testaments to how rich India's wildlife really is.
So, there you have it. This amazing domino-like system. Climate shapes vegetation, and vegetation supports wildlife. But you know the old saying, a chain is only as strong as its weakest link. And this entire natural system, as incredible as it is also incredibly fragile. It's balanced completely on the health of its forests.
So why are the forests that critical link? I mean, what do they actually do? Well, they perform functions that are essential for pretty much all life. They release the very oxygen we breathe, they bind the soil together to stop erosion, they give us countless resources like timber and medicinal plants, and of course, they are the foundational home that supports all that wildlife we've been talking about.
And that brings us to the final, and honestly, the most important question of all. Now that we know how vital and just how fragile this whole balance is, what's our role? What part do we play in protecting it?
Well, the good news is there are really clear, actionable things we can all do. It starts with the absolute basics: plant more trees and protect the ones that are already there. We can get involved in community programs like Van Mahotsav to make an even bigger impact. And this one is huge. We can make conscious choices about what we buy, refusing to purchase anything made from animal parts like horns, fur, or skins. That stuff just fuels illegal hunting.
I want to leave you with this really powerful idea from a story about a girl named Leela. Her parents planted a tree for her on every single birthday. So by the time she was 20, she was surrounded by 21 beautiful trees, a small forest of her very own. It's such a simple act, but it leaves us with a really profound question. What would our world look like? What if we all did the same?